All right. So skills review here. One skill that we need, for example, if you have something like that, guys. How do you compute this on the calculator? Or how you enter it on the calculator? So let me show you. You do 7, and you can try it with me as you divided by square root. You have to press the second key and the x square and put square root of 13. To exit out of the square root, guys, this is what you do right here. And then hit enter. And that's the question. What I noticed, guys, on the test that many of you did not pay attention to the direction and rounding. And that's why I went back and readjusted the scores of many of you. You'll notice some of you had their scores raised a little bit because I reviewed it. And if I noticed some errors in rounding, or if you made a mistake in one part, but then you did the second part right, but based on the mistake that you make in first part, I just gave you a few points here and there. So just pay attention to rounding. If you are to round this one to 2 decimal places, it will be 1.94. If you are to round it to 1 decimal place, will be 1.9. So just pay attention to those things. Another one you need to know also. How to enter this into your calculator. 7.1 minus 6.5 divided by 3.5. Here's how you do it. Okay, if you want to do it in one shot, guys, you have to put parentheses in the numerator. Otherwise, if you don't put parentheses, look what happened. This is wrong. What I'm doing is wrong right now. You know what the calculator knows that the division comes before subtraction. So the calculator divides 6.5 by 3.5 first, but that's not what we want. We want to subtract the two numbers in the numerator and then divide by 3.5. So to do it right, to clear the screen, guys, you just hit. Students asking about clearing the screen right here. So put parentheses, 7.1 minus 6.5 divided by 3.5. And here you go, that's the correct answer now, if you do it this way. Some more skills review for this chapter, guys. Changing decimals to percent. So let's say you use your calculator and you ended up with this answer. 0.3412. You want to change it to a percent. To change it to a percent, guys, you just multiply by 100 and put the percent sign, or move the decimal point 2 digits to the right and put the percent sign. So this will become 34.12%. Okay, so this is very much the algebra that you need for this chapter. And in particular, this, you're going to see that in section 5.4. You're going to come across numbers like that, and you want to know how to use a calculator to find it. All right. So, chapter 5. Okay, first of all, I want to show you this shape, guys. This is a histogram. Can someone give me a description, you know, of this histogram? What do you think it looks like? What kind of shape?
Symmetric.
Symmetric, okay. And what else?
Bell-shaped?
Bell-shaped, all right, let's see. It looks like, yeah, if you try to connect, you know, just the tops of each bar. Okay, it looks, if I have so many thin columns, you know, stacked together, it probably look like a bell-shaped curve. Yes, it is a symmetric it is a symmetric curve. So, and this is, they call it from now on, guys, it's bell-shaped curve. And in the book, they call it the normal curve. So normal means bell-shaped, means symmetric. The mean, guys, is right here, right in the center. This is the x-axis. And this is where the mean is. And actually, it is the mean and the median and the mode. Why the mode? Because the tallest bar is right there. But all what we are interested is in the mean, guys. So it's enough to know that this is called the mean. In real life, guys, for your information, any data that you collect and you try to graph it as a histogram, it's gonna turn out very likely to be bell-shaped. That's how things are in life. For example, if we collect data on how much people spend on gas each week, you're gonna notice that the majority of us spend pretty much the same. There are a few of us who spend so little, and there are a few of us who commute long distance, probably to work another place, who spend too much. But the overwhelming majority spend pretty much, the same. And then if we graph the data that we collect, it's just gonna have this shape. There are some data we collect that they turn out to be skewed right or left or not. They're not symmetric. But as I'm telling you guys, most of the data sets will turn out, to have a bell shape. And that's why this kind of distribution that we are studying today is very, very important distribution, because it does reflect on us. Okay. In chapter 4, you learn about binomial distribution using the discrete random variable. A discrete variable means it is countable. We can count it as 1, 2, 3, 4. There are no decimals, only whole numbers. That's why I told you chapter 5 is not related much to chapter 4, because we will not be using discrete variable. We are using continuous variable. A continuous variable has an infinite number of possible values that can be represented by an interval on the number line. So they're not discrete. A continuous is something that can have infinitely number of possible values. For example, weight. This is continuous. Even guys, if you step on the scale now and tell me I weigh 135 pounds, the question is it exactly 135 pounds? And if you want the answer is no. You only read 135, you see the 135 pounds because the scale is customized to only show whole numbers. I wouldn't know if this was 134.99 and it was rounded to 135. So there is nothing called exact weight. But is there something called exact number of students attending my class today, guys? Yes or no?
Yes.
Yeah, there is exact number of students. I can see it right there. I see 23 students there. But not your weight. Your weight is not exact, never exact. Your height is not exact, it's continuous. You go to the doctor's office and they measure your height and they tell you, let's say, 4 inches or 5 inches. Is it exactly 5 foot five? Is it exactly 5 inches? No, it's not exactly 5 inches, but that's what they approximate it to be. So there is nothing, just called exact when it comes to this. Age. Your age is continuous, guys. Even if someone turns 19 today at 12 noon, does it mean that the person is exactly 19 years old? Well, by the time you're telling that person you're exactly 19, already a few seconds have passed. So there's nothing exact with age. So anything, guys, that you cannot count as 1, 2, 3, 4, 5, 6 is not discrete, is continuous. And most of the examples that I can come up with will turn out to be continuous. Your temperature outside today is continuous. Although I checked, before I came to the lesson, and it says it is, -5 degrees, but it is exactly -5. Probably it's -4.9, but the screen that I'm looking at is rounded to the nearest whole number, so you wouldn't know that. So that is a continuous variable. So I'm gonna just list it right there. But the number of pens that I have on my table today, that's not continuous because I can count them. 1, 2, 3, 4. I can't have 4.5 pens or 5.5 or 5.25. If you guys know that you can have a decimal, that means it is continuous. If you know that you cannot have a decimal, then it is discrete. And again, we're not as interested in discrete. It's only the continuous case. Hours spent studying in a day, that is continuous. Even if you tell me, guys, I spend 2 hours a day studying, is it exactly 2 hours? Once you tell me no, then it is continuous. It's not discrete. And ask yourself, can someone spend 2.5 hours? If the answer is yes, then it is continuous. In order for it to be discrete, that means there are no fractions, whole numbers only. When you know your answer can have decimals, then you're talking about the continuous case. So any questions about what a continuous variable is? That's very, very important to understand that. I'm gonna go very slow, guys, with this chapter so you can pick up every bit of it. So the first thing that you need to know is what a continuous variable is, and we will be using data collected from continuous variables only in this chapter. All right. It is the most important. So we'll be talking about distributions of continuous variables, bell-shaped distributions. And they call them the most important continuous probability distribution in statistics. Can you guys help me complete this one? The graph of a normal distribution is called, who's gonna tell me the name? I gave you the name earlier. Okay, let's see in the chat. Normal curve, yes, or bell-shaped. So once someone asks you guys to sketch a normal curve for me, you do this. That's a normal curve, and that's the mean right here. That's the normal curve right here. Okay, let's, I did talk about some of the properties. Let's talk about them again. The mean, median, and mode are what, guys?
All the same.
All the same. Good. The normal curve is bell-shaped and symmetric about the mean. Yes, it is symmetric about the mean. You can think of the mean as a mirror, guys. Half of the data is to the right of the mean, and the other half of the data is to the left of the mean. So it's a reflection, just like think of the mean as being the mirror, and this is a reflection on that, and this is a reflection on that as well. The total area under the curve is equal to what? Remember, the sum of all probabilities, area means a probability. So sum of all probabilities cannot exceed, let's see what we have here, 1. Very good. You can never have sum of probabilities to exceed 1. It's 1. All right. I like it to look at this right here. Okay. And maybe you can help me write the next conclusion. The normal curve approaches, but never what? What do you think the word is going to be? Look at it right here. And this is the axis.
Touches.
Touches. You look at the blue one, you tell me it looks like it touches. Just the technology can't just do that so precisely. That's why, but it doesn't touch. So it does not touch. So it continues indefinitely to the right and indefinitely, but it's very, very close to the x-axis. It's barely nothing, just in between, but it doesn't touch. Let's show you some examples of the normal curves, which you already are familiar about this from section 2.4 when we did the empirical rule, but you can forget about the empirical rule because you're going to be able to do everything with this now. All right, look at this. This is a normal curve, guys. The mean is 3.5 and he tells us the standard deviation is 1.5. That's the mean right there. Standard deviation is 3.5. This point right here, the curve, like you can see, it's just like pointing up, and then here it's switching, pointing down. They call it an inflection point. You don't have to worry too much about it. Just know the shape of the curve. So that the mean is 3.5, and he tells us that the standard deviation is 1.5. How many standard deviation, guys, above the mean we have to move until we reach almost the end of the curve? Who can answer this question? 3, exactly. So 1.5 plus 1.5 plus 1.5 will be 4.5. Added to 3.5 will be 8. Very much like here. You'll reach almost then. And the same thing, guys, from the other side, you subtract to a 3 standard deviation. This is still the case. Look at this one, guys. You notice the mean is the same, 3.5. But even without looking at the standard deviation, I know, guys, that this curve has a smaller standard deviation without even looking at the value. How do I know that? Can someone tell me? This has a smaller standard deviation than that. How do I know this? Not taller, not the exact. Probably I know what you want to say, but it's not the exact word taller.
Not as wide?
Yes, narrower curve. Yes, because it could be taller and wide as well, but narrower, yes, it's smaller standard deviation. All right. Now I'd like you to look at the third shape, guys. They're exactly the same opening, so probably they have the same standard deviation because the data is spread exactly the same in both of them. But look what they have in difference. This mean is 3.5 here. He moved the curve to the left. The mean is what? 1.5. So in other words, guys, you could have two normal curves that have the same mean but different standard deviation, or you could have two normal curves that have the same standard deviation but different means, and you can have two normal curves that have different means and different standard deviations. So how do you sketch the normal curve, guys? I'm going to give you this hint, because one of the questions when you start working on chapter 5 is going to tell you which one is the correct normal curve. He's going to give you the mean and the standard deviation, tell you, give me the graph of the normal curve. Look how you do it. Let's say he says the mean is 5 and the standard deviation is 2. Look, how do you check which graph is the correct one? You look, first of all, for this shape. It has to have this shape. You look for the graph that has a 5 here in the center. It has to have a 5. And then you look for a graph that has a three tick marks that takes us to the end when we add 6. And if you ask me why 6, you add 3 times the standard deviation. So this is a 7, this is a 9, and this is an 11. And then this way, guys, it's going to be a 3, a 1, a -1. And that's how you can tell. So if you see something similar to this one, then you know this is the correct graph. You go 3 standard deviation above the mean and 3 standard deviation below. It turned out to be with a negative. That's fine, but likely won't work with negative numbers. So he will give you the mean, for example, 15. Let's say make it 15, guys, here. And then if it is 15, that's 17, 19, 21. And now it's going to be 13, 11. And now no negative numbers. It's 9. This is the normal curve. Any questions? All right. If I ask you which curve has a smaller standard deviation, guys, let me just chart 2 of them. This is 1. You should be able to answer this. So this is A, this is B. So which curve has a smaller standard deviation, A or B? B, exactly, because it's a narrower curve. You don't need to do the math. Even if he gives you the data set, you don't need to plug them into your calculator and try to figure this out. And actually, this was one of the questions on the test. I gave you 3 histograms and I asked you which one has a smaller standard deviation, larger standard deviation. All right. So this is definition of the normal curve. Okay, guys, help me out. Which curve has a greater mean, greater standard deviation? So greater mean. Greater mean, you just have to read it. And which one has the greater mean? So A or B?
A.
A, yeah. Look, the mean for A is 15 and the mean for B is 12. Greater standard deviation. You guys agree it's B because the data is more widely spread. Now, what is the standard deviation? I don't know. I can tell the mean because it should be on the axis, but not the standard deviation. But if he gives me 2 standard deviation, I'll pick the larger one and I know it's for B and the smaller one is for A. Any questions, guys? If the book says that, that's a different example. Probably I switched, the number. It can't be. The greater mean is for A because it's 15. Look, this is the mean for A. That's the mean. And look, this is the mean for B. So this is the mean for A, and this is the mean for B. So the greater mean is for A. Okay? Any questions? Yes, that try to yourself could be different. Yes. Standard normal curve, Z-scores. That's we're gonna try to, I'm gonna refresh, just your memory of what the Z-score is. That's very, very important. Those tools, guys, are gonna make your learning of this chapter very straightforward once you pick them up. So far we learned what the normal curve is. It's a bell-shaped curve that has a mean in the center and that has a standard deviation. And the total area under the curve, it's always 1. See, the area is 1. Now, what does he mean by 0, 1, 2, 3, 4, 5, 6, 7? Let me just remind you of this. This is something that we did in section 2.4. I'm just going to do it again. So if you forgot about it, not a big deal. Let's say we have this bell-shaped curve, guys. So I'm going to sketch one. And let's say the mean is 100 and the standard deviation is 10, just for convenience. So I'm going to sketch this curve. When he asks you to sketch the normal curve, guys, just do 3 standard deviations to the right and do 3 to the left. That's what he wants. So can you guys help me? Tell me what the numbers are going to be. Sigma is 10, remember. So what are the tick marks? 110,
To the
120?
right, 110, 120, 130.
Yep,
And to the left, 90, 80, 70.
correct. And this is called the normal curve. Now let me get another index card and show you what the standard normal curve is. So I'm gonna sketch it right here. Please pay attention to this. That's very, very important. So I'm gonna sketch the exact same graph, guys. Okay. There's the Z-score. The Z is value minus mean divided by standard deviation. That's the Z-score. The Z-score will tell us how many standard deviation does a value deviate from the mean. How far apart is a value from the mean? For example, what's the difference, guys, between the mean 100 and the value 110? The difference is 10. How many standard deviation is this? Sigma is 10, so it's only one standard deviation. So the Z-score for 110 is 1, because 110 is 10 points away from the mean, and 10 is one standard deviation. What do you think of 120? How many standard deviation is this, guys? It's going to be 2. And what about 130? It's a 3 standard deviation away from the mean. What about the mean itself? How much does the mean deviate from itself? What would be the Z-score for the mean?
0.
0, because it's only, the mean is right at the mean, so there is no deviation. What about 90, guys? The difference between 90 and 100 is 10, which is one standard deviation. But remember, this is from the left, so instead of saying 1, we're going to use what?
Negative.
Negative 1, exactly. And this, guys, is going to be negative 2, and this is going to be negative 3. So you can redraw the normal curve using this technique, guys. Instead of putting 100, 110, 120, 130, 90, 80, 70, look what I'm going to put. The black, the one in black is exactly the same in red, but this is called the normal curve. This, guys, when you use Z-score, is called the standard normal curve. Here the axis, it's called the x-axis. Here the axis, guys, is called the z-axis, and we'll be using the z a lot. It's easier, it's more convenient. The 0 here represent the mean. And guys, don't think that this means that the mean is 0. No, the mean is 0. It just means that the mean deviates 0 standard deviation from the mean. The 1 means that this value deviates 1 standard deviation from the mean. 2 means that the value deviates 2 standard deviation from the mean, and so on and so forth. So this is called the standard normal curve, and this is called the normal curve. So if you are asked a question, what is the difference between the normal curve and the standard normal curve? You say the following. The normal curve has a mean and a standard deviation. The standard normal curve has a mean 0 and standard deviation of 1. So here we have a mean and a standard deviation. For the standard normal curve, the mean is 0, which is right at the center, guys, and the standard deviation is 1. So 0, 1. We will be using the standard normal curve because it's a lot easier to use than the normal curve. And remember that when you have a sketch that has a 0 right at the center, remember it's not the normal curve, it's the standard normal curve. Any questions? All right, here you go. Any x value can be transformed into a z-score by using the formula value minus mean divided by standard deviation, and I put it there. If each value of a normally distributed curve is transformed to a z-score, then we have what we call the standard normal curve. And that's what I explained to you guys earlier. This is the normal curve right here. And this is the standard normal curve right there. You see the 0 right in the center and sigma equals 1. Here you have a mean mu and sigma. It's exactly the same curve, the same shape, the same narrowness, everything exactly the same. The only thing that changes are the labels on the horizontal axis. You see this one is called the x-axis and this one is called the z-axis. Okay. You know, in real life, guys, you cannot compare apples with oranges because they're not the same. But if you change each one of them to a z-score, then you can compare them. That's why it's important to learn what z-scores, because z-scores don't have any units. And if you have two different quantities that cannot be compared, there is a way to switch them to z-scores, then you can do the comparison. And that's why it is important to understand what z-scores is, because the z-scores tell you how many standard deviation does the value deviate from the mean. Is it more above the mean, below the mean, etc. If the z-score is positive, the value is above the mean. If it is negative, the value is below the mean. If it is 0, it's exactly the mean. So for example, had I said like to one of you that your z-score on test 1 was 0, I don't want the students to panic. All I'm trying to say that your score was exactly the average of the class. That's what the z equals 0 means. Okay, use the standard normal table to find the area to the left of z equals 1.15. Okay, now we're coming, just to the real stuff. So let's get ready for this. Probably have a question here. Let me. What is the area to the left of 0? This area. If I shade it, can someone tell me? You should know.
Negative.
What is it? Area. Remember, the area is between 0 and 1, 100%. Can't exceed 100%. Total area under the curve is 100%. If I just shade to the left of 0, what would be the area?
50%.
50%, exactly. It's half. It's 50%. It's a probability. Remember, guys, when I say area, it's a probability. So what's the chance? What's the percent? What's the proportion? It's all the same thing. It is a probability. And you guys, you would agree with me if I tell you the area to the right of 0 is also 50%. And actually, guys, there's something that you learned in chapter 2, and you know the answer already if you still remember it. Does anyone still remember what was the area between -1 and 1? One standard deviation above the mean, one standard deviation below the mean.
68%.
The 60-80%. But you guys, the good news is you no longer need to memorize any of this because we're going to learn how to find those areas. Okay, so let me put this in here. I'm going to put any number and show you how we're going to find the area using two techniques, using technology and using the table. So this is the 0, this is the z, and I'm going to put 1.15. So 1.15 has to be above 0, guys. So I'm just going to make it right here. And he says, find the area to the left of z. So you guys agree with me, to the left of z equals 1.15. I have to shade to the left. All right. We're going to learn how to find this area. Let me ask you a question first. Do you guys agree with me that the answer is going to be over 50%? Yes or no?
Yes.
Is it clear to all students why it's over 50%? Because look, at 0, it's 50%. This one right here, this is 50%. I shaded a little bit more than 50%, so it's going to be more than 50%. There are two ways to find this area, guys. If I give you 4 choices and 3 of the choices are less than 50%, you can, guys, close your eyes and pick the one that is more than 50% because we know it's going to be more than 50%. But it's not going to be like this. There are 2 ways to find the area under the curve, either using technology or using the table that I showed you a little bit earlier. What I'm going to do, guys, I'm going to try to show you how to use the table first and then go to technology, but I'm always going to give you the choice to either use whatever you want. If you feel comfortable with technology, use it. You want to use the table, that will be an option. So just give me a second.